Let's go on to aldol additions. We're stepping back to section 3 now. And let's remember that when an aldehyde is treated with hydroxide or an alkoxide, the equilibrium forms where a significant amount of both enolate and aldehyde are present, right? So using hydroxide or any other methoxide, ethoxide is an equilibrium reaction to create the enolate. Now, if the enolate attacks the aldehyde that's still present, then an aldol reaction occurs. So we are going to be using a weak base here. A sodium hydroxide is common. Methoxide is fine. Ethoxide is fine as well. Why we are doing that is because both the enolate and aldehyde are present, and we want two equivalents of our aldehyde to react, one in the enolate form and the other in the aldehyde form. And we create a new alpha beta bond in this reaction. And we create, at this point, we'll see that it is a beta hydroxyaldehyde. The product features both the aldehyde and the alcohol group, which is why it's called aldol. The location of the alcohol group will always be on that beta carbon. Under basic conditions, an enolate is the reactive intermediate. So this is always going to be done under basic conditions. So in that first step, we'll do a proton transfer where we attack the alpha carbon to pop a lone pair on that alpha. And then this is where it's in equilibrium with other aldehydes. We take a second equivalent of aldehyde and we can do a reaction at the carbonyl. That carbonyl is going to become the beta of the product. So alpha beta bond is formed in that second step, the nucleophilic attack. And then proton transfer to make the beta hydroxy. The aldol addition is an equilibrium process, so most often simple aldehydes produce the aldol product is favored. For most ketones, the aldol product is not favored. And so there is a reverse mechanism that is able to occur as well. What we do to mitigate the reverse reaction or the retroaldol reaction is actually use a condensation reaction. Now, typically we will see that these condensation reactions, we are going to do them under basic conditions. You can do them under acidic conditions, but we're going to deal with just basic conditions. Now, an aldol condensation reaction has a little bit extra to it. An alpha beta unsaturated aldehyde or ketone is formed. So these alpha beta unsaturated carbonyl forms will be our products, and it's because heat is going to be added. We're driving off water in this reaction. So an aldol condensation occurs when an aldol addition is performed, and then we elevate the temperatures. We do it at very, very high temperatures. Water will be driven off. Aldol condensation is better for us because it is irreversible. So where aldol addition, which was sodium hydroxide in water, produced the beta hydroxyaldehyde. Simple aldehydes work with this. Ketones, not so much. The aldol condensation works for aldehydes or ketones, and the only addition that we have is heat to make that alpha beta unsaturated aldehyde or ketone, and it's irreversible. So let's go ahead and look at that mechanism. We're going to start at the whole thing, all right? So starting with aldol addition and then follow it up with the elimination of water. Aldol addition, let's go ahead and deprotonate that alpha carbon. Let's do our nucleophilic attack to add on our beta position. There's that new alpha and beta bond. And then we will protonate our oxygen on the beta carbon to produce the alpha beta beta hydroxy aldehyde. Then for the elimination of water, a second equivalent of hydroxide is going to be used to make another enolate. Still same pKa, right? So we can still deprotonate that in an equilibrium reaction. Just now, in basic conditions, we have a loss of a leaving group. We complete that elimination style reaction where the hydroxide is ejected to create the product, the alpha beta unsaturated aldehyde. When cis and trans or E and Z is formed, typically we will only show the major product, which is the trans form or E stereochemistry. Because the aldol condensation is favored, it's often impossible to isolate the aldol addition product. And so really how we would even want to think about only forming the aldol addition product is at ultra low temperatures. So 10 degrees Celsius, we can get 20% product. We probably don't ever want to do that. I hope at this point in your academic and organic chemistry career, you're looking at 20% as like, that's probably not good. So typically we usually only do aldol condensation reactions at high temperatures. We get much better yields. We can have crossed aldol reactions where we have a mixture of two different aldehydes and ketones to create the desired product. It's called crossed aldol or sometimes called mixed aldol. The problem is if you just throw in two different aldehydes or two different ketones, you can get a maximum of 4 different products. Like, look at all these different products. Like, why would we want this? This is probably not a good idea, right? To just throw them in. So we do need a controlled setup. When would crossed aldol reactions be helpful? Well, they're only practical if the number of products can be minimized. Okay, so it's achieved in one of 2 ways. First way, if one of the reactants, the substrates, is relatively unhindered and without alpha protons. So this would be formaldehyde is a great electrophile because it's unhindered. There's not a lot of bulk around this carbon, which would become the beta carbon. Right? And also there's only one alpha on all of these carbon molecules. There's only one alpha position. So there's only one enolate that could technically form. So what we see is that the only compound that can form an enolate is at this position, right? We would see that enolate form and then attack. Again, here's another one. Attack another aldehyde that does not have the ability to form an enolate. That can either be formaldehyde or it can be benzaldehyde here, where the alpha position is not valid because there's no hydrogens there. All right. If you use LDA as a base, it's called directed aldol addition. So you take one aldehyde or ketone, you react it first, step number 1, with LDA. That forms the enolate that you desire. Then step number 2, you sprinkle in the aldehyde or ketone that you want to cross with it, right? And then that forms that beautiful alpha beta new bond. And then you can either use heat and water, or you can try and achieve the aldol the aldol addition reaction only. If you add heat, then you would do the alpha beta carbon carbon double bond product. All right, so one carbon is completely converted to enolate with LDA. That is the irreversible enolate formation. And then the other carbonyl compound is then slowly added in. Just sprinkle that in like sprinkles on top. Yeah, intramolecular reactions can definitely form cyclic compounds here. Usually it's only going to do it if you have a 5 or 6 membered ring. One group forms the enolate that attacks the other group. So typically symmetrical molecules are utilized. And again, alpha of one can then go and attack the carbon of the other carbonyl. And so 1, 2, 3, 4, 5 in between those two positions. 1 here was alpha, 2, 3, 4, 5. Here's beta for the unsaturated position. Clyazine condensation reactions are very, very similar to aldol condensation reactions. The only difference is that we are going to use esters. Esters also undergo reversible condensation addition reactions. And so we tend to try to use a clyazine condensation that is simple. All right, so it is going to look like a nucleophilic acyl substitution reaction. Again, chapter 20, just right here in the forefront of our mind when we're looking at an enolate nucleophile attacking an electrophile. So clyazine condensation reactions, the nucleophile will be the enolate of the ester, and then the electrophile will be a second equivalent of ester. Just like we had 2 equivalents of aldehyde or ketones in aldol reactions, we can have 2 equivalents of esters. What forms is a beta keto ester. Notice here that H3O plus workup. This is an acid workup because we are forming a beta keto ester, which is an extremely acidic position, right? pKa of around 10. And so we need an acid workup to make sure that at the end of the day, our alpha position is protonated and our molecule desired is neutral, not another enolate. So let's go ahead and walk through this reaction. It will look very, very similar. We tend to use an alkoxide here, one that will match in our groups to the ester. That way we won't get any competition with esterification reactions. That would not be fun. We want to react here at the alpha position. We form an enolate, and then the alpha carbon will attack another ester's carbon of the carbonyl, which we will call beta. Awesome. And then instead of protonating this oxygen on the beta position, what actually happens is the acyl substitution reaction. We kick out OR -1. We can do that here in this reaction because we are in a base and it is the same base as the leaving group. And so therefore, the alpha beta position is going to be a beta ketone, right? And we still have our original ester. Now we do have a last proton transfer step because now we have created an alpha carbon that is more acidic. So this is our final product after step number 1. It is the deprotonated alpha position, and it's doubly stabilized by both carbonyls, so it's extremely stable. Now, the last step is what drives the reaction to completion. So you do have to show that, even though you're like, Lauren, come on, I'm just going to put that proton back on. No, that is the last step that is driving the reaction forward. An acid workup is necessary in step number 2 so that we can isolate our neutral product, so that we can pop the proton back up on that alpha position. But it is really important to know why we have that acid workup. Some limitations to clyazine. The starting ester must have 2 alpha protons because removal of the second proton by the alkoxide ion is what drives the reaction forward. So hydroxide, and so if we did not drive that reaction forward with the last deprotonation step, we wouldn't get the clyazine reaction. Hydroxide cannot be used as the base because of what we noted before. We'd get competition with acyl substitution with the original compound itself. And so instead of an ester, we'd form a carboxylic acid, and then we'd neutralize all of our molecules by making the carboxylate ion. And we don't want to do that. So choose a base that is the alkoxide that matches your ester alkoxide. Last limitation here is looking at that alkoxide that matches. Otherwise, transesterification could happen too. So it's not only just using an alkoxide that's important, it's using an alkoxide that matches. We don't want this reaction to occur where we have competition for our enolate formation with transesterification. We just don't want that. Why would we want to compete? So if you have OET as your ester, use OET minus 1 as the base. Very, very simple. Match it up. Cross-Claisen are also useful if, again, very certain criteria is met. One ester has no alpha protons. Again, keep it simple. Or again, we can use direct Claisen condensation with LDA, very similar to what we just saw with our aldol condensations that were crossed. Intramolecular Claisen actually just have a very fancy name. It's called the Dieckmann cyclization. Like aldol reactions, this cyclization prefers 5 and 6 membered rings. It occurs the exact same way. We form the exact same style things, alpha beta or beta keto esters.